This time I'll give a short introduction to Goppa Codes. So let's see what the setting is. So we have a polynomial g, which is over the field fl to the m, where we also write q as l to the m, and it should have degree t. Furthermore, we take elements alpha 1 to alpha n in fl to the m, so in fq, and we want that g of alpha I is non-zero for all I in 1 to n. Okay, now we define the Goppa code gamma of Lg is just the code words C in FL, then to the n, such that the sum from 1 to n, Ci divided by x minus alpha I is 0 modulo g. So now let me first make some remarks. So first note that x minus alpha I is invertible modulo g, because g of alpha I is non-zero, and this polynomial has degree 1, so we can apply the Euclidean algorithm and we get that the greatest common divisor is 1. Okay, and so that's why this equation makes sense, and then we get the code here with the code word C. And that's the general setting. Now we want to look at a special case, namely binary Goppa codes. So now we let L be 2, so that is Q is equal to 2 to the m, and furthermore we let G be square-free. We'll see why we wanna have this now. So then we have a theorem, namely that, actually I think I'd rather say doesn't make much of a difference. Oh, I should have written what L is. So L is just, where do I write it? So L is just a list of alpha 1 to alpha n, so it's a ordered set. Okay, so we could also write gamma of g alpha 1 to alpha n. Okay, and now let's see the statement. So the statement is that in the binary setting, where L is equal to 2 and g is square-free, that the Goppa code with respect to g and L is equal to the Goppa code with respect to g square and L. and we call G the Goppa polynomial. That's just a name we give it. Okay, so now let's prove this theorem. So one direction is easy, so let's prove the first inclusion. So let's say we have a code word C, and then we look at the sum over the Ci divided by x minus alpha I, and we assume that this is 0 modulo g squared, and then it's also 0 modulo g. This is immediate, so there's not much to do. And this gives us this inclusion, so that the Goppa code with Goppapolynomial g squared is a subset of the Goppa code with Goppapolynomial g. Okay, that's the first part. Now we need the other direction. So let's see what we can do here. So now let's assume that the sum I is 1 to n x minus alpha I. This is 0 modulo g. So a first thing we might want to try is maybe we can square it and see what we have. So we get, and let me also mention that this won't lead us directly to a proof, but it gives us a hint of what we should do. So if we square everything, we just get this equation modulo g squared. So now what can we do? Well, we are in characteristic 2, so let's use this. So we get sum I equals 1 ci squared x minus alpha I squared. And now, it's also 0 mod g squared, but we don't need this now. So let's note some things. So at first, note that ci, so here we have an fl to the n, now l is 2, so these ci's are just 0 or 1. So actually the square doesn't matter in our case. For the ci, for the x minus alpha I, it does matter because that's in f2 to the m. And now let's see a little bit further. So we can also sum just over the I, where ci is 1. And then we get 1 over x minus alpha I squared. Okay, and then we could try to go further, but probably this won't lead us anywhere, so I just did this to show you what you can do to see that to see some things for, like, so what we also see is probably, well, we could have recognized it from the start, but also this here we could write it as sum I, where the ci are 1, which is just, so we could write this set also as the support of C. It's called the support. Then 1 over x minus alpha I. So this is this thing here, and this is 0 modulo g. Okay, and now let's go on. So what can we do now? Well, this part with squaring didn't lead us. This doesn't look too good, so let's see what can we do. So now there's a trick, and namely the trick is to define a polynomial f where we just take the I where ci is equal to 1, and then we take the product over the x minus alpha I. And now let's look at the derivative of f, which is just the sum over the I where ci is 1. Then we get a product over the j not equal to I where cj is 1, then x minus alpha j. And now we take f prime divided by f, and that's sum I where ci is 1, and then we get 1 over x minus alpha I. So this is our what we want to look at in the first place. So we get that this is 0 modulo g. Okay, so that's good so far, because that means we can express this term here in terms of these polynomials f prime and f. And now we can use properties of polynomials. So the first property we use is that the greatest common divisor of f and g is equal to 1. Why is that? Well, let's see. We assumed, so in the beginning, that g of alpha I is non-zero. So this gives us that here we have just a product over x minus alpha I, that this greatest common divisor is 1. Okay, so that's the first thing. Then we use Bezout's lemma or the extended Euclidean algorithm, so we get u and v such that uf plus vg is equal to 1. Okay, that's clear, and now let's go on. Now we use another trick, so now we look at uf prime, and that's uf prime divided by f times f. Okay, and now let's see. So we can also write this as uf times f prime divided by f. Now let's look at this modulo g. So let's see. So we have here uf modulo g, we get 1 because this term is 0 modulo g, the second term. So this is 0 mod g. So we get that uf is 1 modulo g, so we get that this is f prime divided by f modulo g, and we've already shown that this is 0. Okay, so That's good, because now let's see, what does this mean? This means that G divides F prime. At first we get that G divides U F prime, but we see from this equation that G is coprime to U, so G has to divide F prime. Okay, and now we know that F prime is a square, so let's see why. So if we have, let's say, F sum from 0 to, well, let's say k. I think we haven't used k. I hope so. So we have fk x to the k, then we get that f prime is sum from 0 to k, k times fk to the x to the k minus 1. And now we get that this is just the sum. Oops, that's completely wrong. Sorry. Fi x to the I, and here, oops, so here I times Fi x to the I minus 1. Okay, and now we have the sum just over the I, which are odd, because the even i's are 0 in characteristic 2, so we have I times Fi, or we can just say 1, because if it's odd it's 1 modulo 2, and so we get that x to the I minus 1 and x to the I minus 1 is, or I minus 1 rather, is even, so this is a square, and because we are in characteristic 2, we can just take squares out of the sum, and we get that f prime is also a square. So yeah, that's it. We could also, yeah, maybe let me write it so we get, let's see, I equal 0 to, let's say, k over 2, and then we get, or maybe let's call it j, and then we get 2j plus 1 times f 2j plus 1 x to the 2j, and now we get, this is the sum over this, and then, or this 2j plus 1 is just 1, and so we get f 2j plus 1, then xj, and then we get a square. Now let's see what we have to do here. So f, let's see, so f is just this product over the x minus alpha I. Okay, so I'm not 100% sure. Probably we need to take a square root here. maybe we can do something about it, I'm not sure. But taking the square root is no problem actually, because if we have, let's look at let's say the map phi from a field, let's say k to k, where phi of x is x squared, and the characteristic of k is 2, then we know that this is a group homomorphism. So phi is well, actually it's a field homomorphism, and then we get immediately that it's injective, or you can also check it by hand. And then if k is finite, we get that phi is a bijection, and in our case the fields are finite, so we get that we can take square roots here. Okay, well, that was actually a little bit more than I wanted to say about this, but well, now we have the complete proof that f prime is a square. So let's take a short reminder. So we have g divides f prime, which is a square, and now another reminder, so the proof is getting rather long. So g is square free. So we get that actually g squared divides f prime. Okay, so that's great, because what does that mean? That means that, let's write it like that. So f prime is g squared times some q, and so we get it f prime over f is equal to r a q over f times g squared, and this is 0 modulo g squared. So also note that dividing by f is no problem, because f is coprime to g squared. So that's what we have here. So we get that from f prime over f 0 modulo g, that f prime over f is 0 modulo g squared, and f prime over f is exactly the thing we want to look at. So that finally finishes the proof. Okay, so let's give a short recall. So we proved that the Goppa code with Goppapolynomial g is equal to the Goppa code with Goppapolynomial g squared if the Goppa code is over f2, so if it's binary code, and if g is square free. And this theorem has some applications. So for instance, let's say you want to decode a Goppa code and you want to use the Berlekamp-Massey algorithm. If you use this equation here, you can decode more errors, or at least you get a better bound for the number of errors you can correct with the algorithm. So yeah, maybe one more thing. So Goppa codes are, for instance, important for cryptography, so they appear in the McAleese crypto system, and you can also use them in the dual system, in the Niederreiter system. And yeah, I think that's more or less what I wanted to say today. Maybe we'll see a little bit about decoding Goppa codes in another video, or maybe I'll make another video about the McAleese crypto system, but I haven't thought about it yet, so let's see if I'll make a video about that. So that was a rather long video. I hope you could endure it, and yeah, maybe see you another time. Bye.